Assalamualaikum. So today we're going to discuss some questions on electrostatics. But before we do that, let's look at some formulas from this chapter. Okay, so here we have the first formula, which is Coulomb's law, we can use this formula to find the electrostatic force. Okay, and then next we have the electric field strength, and we have another formula for electric field strength, followed by electric potential. Okay, electric potential. And this is another formula for electric potential. Next, we have the change. Okay, the change in potential energy, followed by potential energy. So this is when you calculate the potential energy between two charges. So you have Q1 and Q2, then you can use this formula. But if you have more than that, then you can use this formula. Okay, so this is the potential energy between charges. And the final formula is electric field strength. So these are the formulas that we're going to discuss today, okay, from chapter 1. Okay, so let's look at the first question. So the first question says that 3 identical point charges of 2.0 microcoulomb are placed on the x-axis. So we have 3 charges, okay, on the x-axis. The first charge is at the origin. Okay, the first charge is at the origin. So we put as Q1, followed by the second charge, which is at to the right, which is x equals to 50 cm. So we have the second charge here, and the distance between charge 1 and charge 2 is 50 cm. Okay, and the third charge is 100 cm from the Q1. The third charge is 100 cm from Q1 and 50 cm from Q2. Okay, the question is asking us to calculate the magnitude and direction of the electrostatic force which acts on the charge at the origin. So they want us to find the electrostatic force. So we know electrostatic force, we can see whether the charge attracts or repels. Okay, so here we have 3 positive charges, and we know when the charges are alike, that means positive positive or negative negative, the charges would repel each other. Okay, so now if we focus on charge Q1, okay, because they say they want the electrostatic force on the charge which is at the origin. So they want to see which force acts on Q1 here. Okay, so we know Q1 is influenced by Q2. Okay, and since Q1 and Q2 are positively charged, so they would actually repel each other. So F12 would move towards the left. Okay, followed by Q1 and Q3 at positive charges, they would repel each other as well, and F13 will move towards the right as well. Okay, so we know to calculate electrostatic force, we can use this formula where K is actually the constant, 9.0 times 10 to the power of 9. Q1 is charge 1 and Q2 is charge 2. Since charge 1 and charge 2 are identical, okay, so they have the same magnitude, so we can substitute in the value, which is 2 times 10 to the power of negative 6. Okay, for Q1 and Q2. And R12 is the distance between charge 1 and charge 2. So here we have charge 1 here and charge 2 here. So the distance between charge 1 and charge 2 is 50 cm. And then we would get F12 is equals to 0.144 Newton. So we've already calculated F12. Okay, and we have to state its direction, which is towards the left. Okay, towards the left, and so we've already calculated F12. Now we can look at F13. So we will use the same formula, but this time the charges are Q1 and Q3 and R13. Okay, so K is the constant, which is 9.0 times 10 to the power of 9. Okay, Q1 is charge 1, Q3 is charge 3. Again, Q1 and Q3 have the same charge. Okay, and R13 is the distance between charge 1 and charge 3, which is 100 cm. Okay, so we will get F13 to be equal to 0.036 Newton. And F13 is also to the left. Okay, now that we've already calculated F12 and F13, we have to calculate the net force, okay, the total force. So the total electrostatic force on charge 1 is F12 plus F13. Okay, as you can see, here we've already inserted the arrows, okay, the arrows above F. That means we are starting to consider its direction. So since F12 and F13 is towards the left, so we have to include the negative sign. Okay, we have to include a negative sign, and we add it up and we get F12 to be equals to 0.19 Newton. So the negative sign here actually represents, or it actually shows that F1 is towards the left. Okay, and then we get the answer to be, so the magnitude is actually 0.18 Newton, and its direction is towards the left of Q1. Okay, so this is how we solve question number 1. So remember, the keyword here is electrostatic force. So when you have identified the keyword to be electrostatic force, you'll be able to identify the equation that we should use and the concept. Okay, the concept where positive and positive charge will repel each other. So both of the charges will move to the left. Okay, so that's for question number 1. Next, let's see question number 2. Question number 2, it says that a 3.0 coulomb charge is at the origin and 9.0 coulomb charge is at x equals to 4 meter. Okay, so it will look something like this. Okay, the 3 coulomb charge is at the origin and the 9.0 coulomb charge is at x equals to 4 meter. Okay, so here, 9 coulomb charge is here. So we have Q1 here and Q2 here. Okay, where on the x-axis can a third charge be placed so that the net force on it is 0? Okay, where can it be placed so that the net force on it is 0? So that means where can we place Q3? Okay, where can we place Q3 along the x-axis so that the net force to be 0? Okay, so we know, we assume, okay, for it to be 0, we know one force must move to the right and another must move to the left. Okay, one force must move to the right and another will move to the left. Okay, so we know we have to place the charge in the center. Okay, you have to place the charge in between both charges so that one can move to the right and another could move to the left, and the distance between them is 4 meter. Okay, so we know F3 is actually, okay, if we have F3 here, electrostatic force 3 here, F3 would be equals to the sum of F31 plus the sum of F32. Okay, but since the net force is 0, therefore, since F3 is 0, so we can show it like this, and F31 will actually be equal to F32. Okay, F31 must be equal to F32 so that our net force can be 0. Okay, and then we substitute in the value. Okay, so the main key concept is for the net force to be 0, the force experienced by charge 3 due to charge 1, okay, force experienced by charge 3 due to charge 1, okay, is moving to the right, and the force experienced by charge 2 the force experienced by charge 3 due to charge 2 is moving to the left. Okay, so we have one to the right and one to the left, so their magnitude needs to be equal. Okay, their magnitude needs to be equal, then we substitute in the equation. So that's why F31 is equals to F32, so it can cancel off each other. That's how the net force can be 0. Okay, once we've identified that, then we substitute in the electrostatic force formula. Okay, so F31 is between charge 3 and charge 1, R3 and R1. Okay, F32 is between charge 3 and charge 2, and R32. Okay, we can cancel off the K because it represents the same value. Okay, and we can also cancel off charge 3, which also be the same. Okay, so we are left with this equation, and when you solve the equation, you will be able to get x is equals to 1.5 meter. Okay, R31, okay, R3 and 1. So for example, we can label this as x. Okay, we can label this as x. So if this is x, the remaining would be 4 minus the x. Okay, 4 minus x, we will get the remaining. Okay, so that's why F31 is x and F32 is 4 minus x. So we get x is equal to 1.5 meter. Okay, so x should be placed 1.5 meter from charge 1. Okay, then we can get equal so that the net force to be 0, and F31 can be equal to F32. Okay, so that's for question number 2. Okay, so 1.5 meter from the origin, okay, which is from Q1 lah. Okay, moving on to question number 3. Okay, question number 3, it says that a 5.0 microcoulomb charge is placed at a 0 cm mark of a meter stick, and a negative 4.0 microcoulomb charge is placed at a 50 cm mark. Okay, so we have 5 microcoulomb at 0 cm, okay, or at the origin, and a negative 4 microcoulomb is placed at a 50 cm mark. Okay, so it's 50 cm, or we can put it as 5 meter. Okay, and then at what point on the line joining the two charges is the electric field 0? Okay, just now we were discussing about electric force, okay, electrostatic force. Now we talk about electric field. Okay, for the electric field to be 0, we have to place another charge closer to Q2, closer to the smaller charge. Okay, the other charge should be closer to the smaller charge. That way it can cancel off each other. Okay, so we know for the electric field strength, so we know a positive charge, the electric field lines was actually coming out. Okay, so we know 3 and 1. Okay, Q1 is a positive charge, so the electric field line will be coming out this way. So it's for electric E31, it will be moving towards the right. Okay, and for a negative charge, the electric field line will be going into the charge. So E32 will move this way. Okay, so we know we can see based on the charge, Q1 is bigger compared to Q2. Okay, so when Q1 is bigger, we need to place the charge closer to the smaller charge. That way it can be equal. That only it can cancel off each other. Okay, so the same concept. So we know the sum of E3, okay, the sum of the electric field on charge 3 is E31 plus E32. Okay, it should be E31 plus E32. But now we have E32 moving to the left. And the net, it says here, the net electric field is 0. Net electric field is 0 and E32 is moving to the left. Okay, so when we rearrange it, we know E31 must be equal to E32. Okay, E31 must be equals to E32, and then we insert the formula, which is KQ over R31 squared. Okay, so KQ1, we substitute the value of Q1. Before that, we can cancel off the K. Okay, we substitute the value of Q1, which is 5 times 10 to the power of negative 6, and X would be 0.5 meter. Okay, X is Q1 and Q2 is 0.5 meter. So here and here would be X minus 0.5 meter. Okay, so here would be, so the distance between them, we can label it as X. You can use any unknown, but it will be easier for us to use X. Okay, and then the remaining is X minus 0.5. So we know here to here is X. So X minus 0.5, we will get X minus, so here we would, the remaining. Okay, so X is the total. 0.5 is between charge 1 and charge 2. So the remaining would be X minus 0.5. So we substitute in the value, and when we solve the equation, we will get X equals to 4.7 meters from the 0 cm mark. Okay, X is equals to 4.7. So the distance between Q1 and Q3 is 4.7 meters. Okay, so this is question number 3. Okay, we can see question number 4. Okay, question number 4, it says that consider a square which is 1.0 meters on a side. Okay, a square is 1.0 meters. Charges are placed at the corners of the square as follow. So we have a square and there's 4 charges, Q1, Q2, Q3, and Q4. Okay, yes, okay, so these are the coordinates given. So when we show it here, it will look something like this. So what is the magnitude of the electric field at the square center? Okay, what is the magnitude of the electric field at the square center? Okay, so to study the electric field strength, so we first can identify the electric field lines. Okay, so we know, okay, for a positive charge, Okay, for positive charges, the electric field lines will always move out of the charge. Okay, the electric field lines will always move out of the charge. Okay, so each EC1, okay, electric field due to charge 1 will move out of charge 1. So it will move upwards. Okay, so the first arrow, this first arrow is electric field due to charge 1. Okay, so it will move out from Q1 because it's a positive charge. Okay, it will move out from Q1, and Q2 is also a positive charge. Okay, so Q2 is also a positive charge. So Q2, the electric field strength will also move out. The electric field will also move out from Q2. So we have EC1 and EC2. Okay, followed by EC3. Okay, electric field due to charge 3. So electric field due to charge 3 is here, and it's also a positive charge, so it will move upwards. Okay, it will move out. And we have a positive charge, a negative charge. A negative charge, electric field will move towards or into the charge. So we have electric field due to charge 4 moving into the charge. Okay, so this is the electric field lines that we have. So we have 4. This is the first one, due to charge 1, due to charge 2, due to charge 3, and due to charge 4. So the keyword, always remember, positive charge, the electric field will move out of the charge, okay, and a negative charge, it will move into the charge. Okay, and we know the distance between them, it's all the same. Okay, the distance between, because it's a square, so we have 1 meter, 1 meter square, so the distance between them is all the same. So we can calculate. Okay, now we want to calculate the distance from here to here. Okay, we want to calculate distance from here to here, and we know we have a triangle, so we can take this one as a big triangle. Okay, we take this one, we have 1 meter here and 1 meter here, so we want to calculate the hypotenuse. So okay, we want to calculate the hypotenuse of this triangle. Okay, so we can use Pythagoras theorem. So we take 1 meter squared plus 1 meter squared, and we divide it by 2. We divide it by 2 is because when we take 1 meter squared and 1 meter squared, we will get this to be the hypotenuse, but the radius is actually just half of it. Okay, I repeat, when we take the triangle, we will get this to be the hypotenuse, but we only want half of it. So this is Pythagoras theorem on top, and the second part we divide it by 2 because we only want half of it. Distance from here to here, towards the center, from the center towards the charge. So we will get R is equals to 1 over square root 2 meter. Okay, and R is the same for C1, C2, C3, and C4. Okay, so to find the total charge at the center, the total electric field at the center, we need to add up EC1 plus EC2 plus EC3 plus EC4. Okay, so if you look closely, you can see EC1 and EC2 are opposite to each other. Okay, and Q1 is also positively charged, and Q2 is positive 4, and Q2 is also positive 4. Okay, so actually since they have the same magnitude and the direction is exactly opposite each other, EC1 and EC2 will cancel off each other. Okay, if you look here, EC1 is upwards and EC2 is downwards. Okay, and they have the same magnitude because both of it is positive 4. Okay, both of it is positive 4. So EC2 and EC1 will cancel off each other. So we get EC3 to be equals to EC4, which is KQ over R squared. Okay, EC3 and EC4 is also the same value because one is a positive charge and one is a negative charge. But since both is moving upwards, so we have to add them up. Okay, so we will get EC3 to be equals to 5.4 times 10 to the power of 4. So we calculate for EC3 first. Okay, we calculate for EC3, we get 5.4 times 10 to the power of 4, and we get the total EC to be EC3 plus EC4. Okay, so we add both of it up. Okay, both of these have the same value because the charge Okay, when we calculate the electric field strength, we do not consider whether it's a positively charged or negatively charged. So since Q3 and Q4 both are 3 microcoulomb, okay, so we will get E3 to be equal to E4. They have the same magnitude. Okay, they have the same magnitude and same direction. So we just add it up. Okay, so EC3 is 5.4, EC34 is also 5.4. So we add it up and we get EC is equals to 1.1 times 10 to the power of 5 Newton per Coulomb. Okay, so this is question number 4. So you always identify the electric field strength direction and see EC1 and EC2 actually cancels off each other. And EC3 and EC4 has the same magnitude, so we can add them up and we get the final answer. Okay, so that's for question number 4. Moving on to question number 5. Okay, so for question number 5, okay, question number 5 is given us a diagram and it says that the electric field at a point 10 cm from charge P is as figure above is 2.7 times 10 to the power of 6 Newton per Coulomb. Okay, so that means they given us the electric field strength of this charge, okay, due to charge P. Okay, so determine the charge P. So they've given us the electric field strength. They want us to find P. So it's actually a very easy question. So we just use the formula, electric field strength formula, which is EQP is equals to, so EQP on charge Q due to charge P is equals to K, charge of P, QP is charge of P, and R is the distance between Q and P squared. Okay, so EQP is 2.7 times 10 to the power of 6, which is given in the question. And we substitute K to be equals to 9.0 times 10 to the power of 9 divided by RQP, which is 0.1 squared. Okay, the distance between them is 10 cm. So we change it to meter, so it's 0.1 squared. Okay, so we get charge P is equals to 3.0 times 10 to the power of negative 6 coulomb. Okay, so it's very straightforward. So they given us this electric field strength, okay, the electric field, and then they want us to calculate charge P. So we just use the formula given. Okay, and then next, okay, it's the same question, but now with a reference to figure above, a charge Q is placed at 10 cm from charge P. So initially Q was here. When charge Q is moved horizontally to the right to a position 5 cm. So initially Q was here and it's moved to the right. Okay, it's moved to the right 5 cm from its initial position. Okay, there is a 0.54 joules change in electric potential energy. Okay, so when we move charge Q from here to here, okay, the electric potential energy changes. Okay, the electric potential energy changes by 0.54 joules. So 0.54 joules is actually change of electrical potential energy. So it has a triangle in front. Okay, change of electrical potential energy. And this is the formula for change in electrical potential energy. Okay, and we know delta V is electric potential. So we can use the formula and open it up to KQ over R. Okay, since we are moving it from Q initially to Q final. Okay, so this is R, distance of R from P final. That means P to final and P to initial. Okay, RP to final. P to final, which is here, and P to initial. Okay, and QP is charge P lah. Okay, so we can factorize out K, Q, and P. So we have charge Q here, and we have charge P. Okay, they've already given us the change in electric potential to be 0.54. So U is equal to 0.54, and K is a constant. Okay, charge Q. Okay, charge Q is what we are finding for, and charge P, we can use our answer from the earlier 3.0 times 10 to the power of negative 6. Okay, the one we got earlier. So we substitute in the value. So P to final, okay, P to final is 15 cm, okay, and P to initial is 0.1 cm. Sorry, 10 cm, which is 0.1 meter. So we can get charge Q is equals to negative. So it's a negative charge. Okay, negative 6.0 times 10 to the power of negative 6. Okay, so keyword is when we move charge Q to from initially to final, we move it by 5 cm. There's a change in potential, electric potential energy. So this is the formula for electric potential energy, and we can open up the formula electric potential to KQ over R. Okay, so this one is for the final part, this one is for the initial part. So this is the final part and this is the initial part. Okay, we factorize out, substitute in the value, and RF is distance between P to final, okay, and R initial is between P to initial, so 0.1, and so we get charge Q to be a negative charge. So we know charge P is a positive charge, okay, charge P is a positive charge and charge Q is actually a negative charge. Okay, so next question, they want us to sketch the electric force vectors on charge P and Q. As I said earlier, we have P and Q. P is a positive charge and Q is a negative charge. So their electric force, they would actually, since they are opposite, they would actually attract each other. So P and Q, P will move towards Q and Q will also move towards P. So they will attract each other. Okay, so this is the sketch of our electric force, okay, between charge P and charge Q. Okay, and finally, question 5, the last part of question 5. So it says that if the charge Q, okay, charge Q is again moved horizontally to the right to a new position, and the electric force on it is 4.0 times 10 to the power of 5 Newton. How far apart is the charge Q and P? Okay, now we've already known the magnitude of the charge. Okay, we know the magnitude of the charge. We know the new electric force. Okay, the new electric force is 4.0 times 10 to the power of 5. They want us to find how far apart. That means they want us to find the distance between P and Q. Okay, so now we are using the formula electric force. This is the formula for electric force. And the new electric force is 4.0 times 10 to the power of 5. So K is a constant. Q is the charge of charge Q, okay, which we got from the question earlier, 6, and charge P, which is 3, okay, divided by the distance between them. So now we are looking for the distance between charge Q and charge P. So we will get the final answer to be 0.2 meters. When you solve it, you will get the final answer to be 0.2 meters. Okay, so that means the distance between P and Q is 0.2 meters when the electric force between them is negative 4.05 Newton. Okay. Moving on to the next question. Okay, so they say there's two positively charged parallel plates and are held 2 millimeters apart. So the distance between two parallel plates are 2 millimeters apart. A 4 times 10 to the power of negative 5 joules of work, okay, is needed to move 2 microcoulomb point charge from one plate to another. Okay, so we have a plate, okay, and the work done needed to move the charge from one plate to another is 4 times 10 to the power of negative 5. Okay, and the plate are 2 millimeters apart. Okay, so we can use this formula and we know, okay, V is actually equals to ED. Okay, so from the formula E equals to V over D, so we can rearrange it to V is equals to ED. Okay, and then we substitute in the information that we know. So we know the work done needed is 4 times 10 to the power of negative 5. Okay, E is the electric field strength. Is the electric field or the point charge. Okay, which is Q naught is 2 times 10 to the power of negative 6. That's the charge. E is what we're looking for. Okay, we want to find the electric field. Q naught is 2 times 10 to the power of negative 6. So 2 microcoulomb 2 times 10 to the power of negative 6. E is the electric field strength which we are looking for, and D is the distance between the plates. Okay, when they talk about parallel plates, okay, then we can use this formula, which is E is equals to V over D. So V is actually equals to ED. Okay, and we will get our electric field between the plates to be equal to 1 times 10 to the power of 4 volt per meter. That's the electric field strength between the plates. Okay, moving on to question number 7. Okay, so we have two charges. One is 5.0 nanocoulomb. Okay, 5.0 nanocoulomb, and another one is negative 2.0 nanocoulomb. Okay, so we have and then we have the charge which is 3 meters apart, and they want us to calculate the electric potential at point P. So we sketch. Okay, we have the first charge which is 5 nanocoulomb. Okay, Q1 5 nanocoulomb, and it's at 0, 0. Okay, it's at 0.0 and 0.0. So we can assume this is 0.0 and 0. Okay, Q1, and a negative 2.0 nanocoulomb charge is at 3, 0. Okay, that means the y coordinate is still 0 and the x coordinate is 3. So that means it's towards the right, 3 meters towards the right, and we have charge Q2, which is negative 2 nanocoulomb. If the potential is taken to be 0 at infinity, okay, potential is at 0 at infinity, the electric potential, what is the electric potential at point P? So this is point P, which is 0, 4. That means the x coordinate is 0 and the y coordinate is 4. Okay, 4. The y coordinate is 4. The x coordinate is 0. So what is the electric potential at point P? Okay, so now we have two charges. Okay, so we have to find the electric potential for each charge. Okay, electric potential for each charge. Okay, so we can use the formula KQ over R. Since it's the same K, so we can factorize out the K. Okay, so for VP1 is charge Q1 over the distance RP1. That means from P to Q1. Okay, and Q2 is charge Q2, and R is the distance between P to charge 2. Okay, which is 5. Okay, so we can substitute in the formula 9.0 times 10 to the power of 9, Q1 5 times 10 to the power of 9. Okay, 5 nanocoulomb, and RP1, distance between P and charge 1 is 4 meters. Okay, for electric potential, don't forget to include the sign of the charge. So for Q2 is actually negative 2 nanocoulomb. Okay, negative 2 nanocoulomb divided by the distance between them. So to find the distance between charge Q and P, we can use Pythagoras theorem. Okay, so we know here is 4 and here is 3. So to find the distance here, we can use Pythagoras theorem. So we take 3 squared plus 4 squared and we square root the answer. Okay, Pythagoras theorem, and we get the distance here to be 5. And when you substitute in the value, you will get the electric potential at point P to be equals to 7.7 volts. Okay, so 7.7. That's electric potential at point P. So the next part of this question is the same question. The next part, it says that the electric potential energy. So earlier we've calculated the electric potential, but now we want to calculate the electric potential energy. So electric potential energy is actually U. Okay, so they want us to calculate the electric potential energy at point P. So it's actually UP. So we know electrical potential energy at point P is equals to QP VP. QP is charge P, okay, charge at point P, multiplied by electric potential at point P. So now this replace point P with a charge, okay, with a charge of 1.0 nanocoulomb. So point P is replaced with a charge, and so we can just substitute in the value QP to be 1.0 times 10 to the power of 9, because at point P, there's a charge at point P. So it's 1.0 times 10 to the power of 9, and VP is electric potential at point P. From our answer earlier, it's 7.7. So we get the final answer, which is electric potential energy at point P, okay, is 7.7 times 10 to the power of negative 9 joules. Okay, and the final part of this question is the same question. Now it says the work required to bring a 1.0 nanocoulomb charge from infinity to point P. So that means here we have point P. So we want to bring a charge from infinity. So from infinity to point P. How much work is required? Okay, to bring a charge from infinity to point P. The charge is 1.0 times 10 to the power of negative 9, because 1.0 nanocoulomb. Okay, so it's the same. We use the formula work done to bring the charge from infinity to point P. Okay, so it's Q naught, but now it will be changed in electric potential. Just now was just electric potential, but now since we're bringing the charge from one place to another, so there will be a change in electric potential. Okay, so from point P, which is the final point, to the minus the initial point, which is at infinity. So we substitute our value. Q naught is 1.0 times 10 to the power of negative 9. Vp is electric potential at P. Okay, electric potential at P is 7.7. And we know the electric potential at infinity. Okay, the electric potential at infinity is 0. Okay, so our final answer, work done to bring the charge from infinity to point P is equals to 7.7 times 10 to the power of negative 9. Okay, so this is the answer. So that's all from me. Thank you.